Minecraft is, in a sense, an Earth simulator, with animals, oceans, mountains, trees, weather, day-night cycle, etc. Of course, there are some differences. On real Earth, you won't find floating trees and armless, cactus-like suicide bombers sneaking up on you. But overall, terrain is designed to feel Earth-like. Have you ever wondered how this terrain is actually generated? Well, I hope so, because that's what I intend to talk about for a while. In the Caves and Cliffs update, we radically changed world generation. The initial goal was to just add big mountains and improve the cave systems. But we ended up changing almost everything to make the world more interesting, more varied, and more dramatic. In the past, terrain generation in games was just magic to me. I didn't understand how it works. But now I've spent a bunch of time working with it and learned a lot. And I find it kind of fascinating how you can do really cool things with just some math and a few lines of code. First, I'd like to talk a bit about size. Minecraft is big. Let's compare with Earth. Earth is a round ball with an area of about 500 million square kilometers. A Minecraft world is a flat square with a surface that is about 3.5 billion square kilometers. So about 7 times larger than Earth. And that is only one world. Every time you start a new game of Minecraft, you will land in a new world. Almost certainly a world that nobody has seen before. Because there are 18 quintillion different unique worlds. That is an 18 with 18 zeros. Let's compare this with our galaxy. The Milky Way has about 100 billion planets. So if each Minecraft world was a planet, we would need about 180 million Milky Ways. It's big. Minecraft is a digital world though, not physical. Digital worlds take less space, but they do take space. Every Minecraft world is a grid of blocks. Think of it kind of like a Rubik's Cube. But instead of 3 times 3 times 3 blocks, it is 60 million times 60 million blocks wide times 384 blocks tall. A digital representation of a Minecraft world is really just a list of which block position contains which type of block. For example, dirt here, air there, water, flower, etc. Storing one complete world would require about 97,000 terabytes. In comparison, the largest disk in the world is about 100 terabytes, so that's not even close to enough space to store a world. If we were to store all 18 quintillion worlds on disk, we would need all hard disk space on Earth times 200 trillion or so. But yet, the Minecraft download is only about half a gigabyte. How can that be? Where are those worlds stored? Well, they aren't stored at all. Not initially. The download doesn't actually include any worlds at all. It contains the code to generate the world. And that code is tiny. In biological terms, you could say that we aren't shipping a body, we are shipping the DNA with instructions for making the body. When you create a world in Minecraft, it looks like you are in an existing world that continues beyond the horizon. But that is actually a carefully crafted illusion. There is nothing beyond the horizon. When you move in that direction, the world gets created in front of you as you go. You can see it happening if you move really fast and the game struggles to keep up. This approach is known as procedural terrain generation. So how does it work? As you may notice, as we move around, the world is generated in chunks. Each chunk is a vertical column 16 by 16 wide and 384 blocks high. The job of procedural terrain generation is to answer a very specific question. What block should we place here? It is basically a function. We can call it getBlock. It takes a coordinate, expressed as x, y, z values, and returns a block. When generating a chunk, we call this function for each position in the chunk. So how do we make each chunk fit with its neighbors? It is like a giant 3D puzzle where each piece just somehow magically fits seamlessly with each adjacent piece, no matter which order we generate them in. We'll get to that. Chunks are actually generated in steps. Here is an example. I made this chunk wider just to illustrate more clearly. The first step is terrain shaping, where we determine which blocks are solid and which aren't, basically just placing stone or air at each position. Then we calculate which of the air blocks are beneath ocean or river or lakes, and fill those with water. Then we apply a surface layer, replacing the top blocks with things like grass, sand, dirt, etc. depending on the biome. Kind of like applying a coat of paint. Finally, we add features and structures, such as trees and ores and villages. In this presentation, I will focus mostly on the first step, terrain shaping. How do we procedurally generate terrain that is random, but also looks somewhat realistic and interesting? Let's start with a very simple example. What if we just make it random? So the getBlock function returns stone or air with equal probability. This is what we get. This is actually procedurally generated terrain. Not very fun or realistic, you can't even get around in there, but it is procedurally generated. But let's tweak it. Instead of just random, let's decide that the surface of the world is at y100. Y is the vertical dimension in Minecraft. So the getBlock function returns stone for positions below y100 and air for positions above. Dead simple. But now we actually get a world that you can move around in. And if we apply surface decoration, we get something like this. Better than before, right? But the world is still all flat and boring though. No rivers, no mountains, no oceans. All the worlds look the same. So our work is not done yet. Now that we have a surface height, we might as well randomly vary it instead of having it fixed at y100. In this case, we say that at each position, the surface height is 100 plus a random number between 0 and 19. One thing about the code examples in this talk, I've simplified the code quite a lot to make it easy to read, skipping all performance optimizations, things such as interpolation and caching. That would be a separate topic. Anyway, now we have a terrain with a random surface height, but it looks kind of messed up, right? There's no continuity or smoothness to it. How can we fix this? Sine curves are actually a good model for this. Here's a graph of sine x. It goes up and down smoothly, and it continues forever in both directions. If we extend it to the left or right, each part of the curve fits perfectly with the part before. What if we generate our terrain using a sine function? Here we go. Surface height is now 100, which is our base terrain height, plus sine x times 10. Sine x returns a value between -1 and 1 depending on x position, which is the east-west dimension in Minecraft. We then amplify the result by a factor 10 in order to make the difference more visible in the terrain. This is what we get. The terrain is basically a sine curve. I'll make it configurable using two variables, frequency and amplitude. And using that, we can easily get terrain like this. Alright, so now we have smooth terrain, and it moves up and down just like in real life. And the code is still very simple. Let's make this sine curve apply to the north-south direction, the z dimension, as well as east-west. This gives us round hills. And while we're at it, why not add a sea level? Let's define sea level as y102. So any position that is above the surface height but below sea level should be water. Cool, now we have a procedurally generated world that is starting to look like an actual world, and still with very little code. But wait, what about the randomness? All parts of this world will look the same. How do we get randomness without sacrificing smoothness and continuity? In 1983, a smart fellow named Ken Perlin came up with a cool mathematical trick, which came to be known as Perlin noise. Imagine a random field of black and white gray dots, kind of like TV static in an old TV set. Now imagine smoothing it out so each pixel is somewhat similar to the neighboring pixel instead of just a random mess. You get something like this, like a smudged version. The general term for this is gradient noise. Perlin noise is just one way of achieving it. This is an example of 2D Perlin noise, that is, 2 inputs and 1 output. The inputs in this case are x and y coordinate, and the output represents the brightness of the pixel at that position. But we could just as well treat this as a height map, with white blobs as hills and the black blobs as valleys. We could generate terrain based on this. Here's an example of 1D Perlin noise. The x-coordinate is the single input, and the y-coordinate is the output. This could be a height map in a 2D side-scroller game, or it could represent the tree height in different parts of the world, or difficulty level, or maybe precipitation levels in different parts of the world. It's really up to you how you use the data, but the approach is useful for all kinds of things. Basically, anytime you want smooth randomness. Let's put this to work in our getBlock function. I'm not going to get into the internal math of how Perlin noise is calculated. There are plenty of third-party libraries that do it for you, so you don't really need to know. So I'll just assume that we have a Perlin noise object as a helper. The code is really simple. We sample the noise at the given xz coordinate, which will give a value between -1 and 1. We amplify it, again, by a factor 20, and add it to the base terrain height of 100. So now the terrain height varies smoothly between y80 and y120. Check it out! Pretty smooth, eh? I can keep going in any direction, and the world will be generated procedurally in front of me, and it all fits together really nicely. For further variation, we can apply a neat trick called octaves. Let's use the sine curve as an example again. Let's pretend this is a Perlin noise graph, and the y-axis is the terrain height. So we have a valley over here to the left and a hill to the right. Okay? Now let's make a second curve, this one with a higher frequency and a lower amplitude. I'm going to call it y2. Let's say that also represents terrain height. So let's add them together, y1 plus y2. And we get this. At a large scale, we still have a valley and a hill, but on a smaller scale, kind of overlaid on top, we get some up and down terrain happening within the valley and on the hill, just like in reality. Let's add a third octave, again with higher frequency and lower amplitude, and add it all together. Now the terrain gets even more interesting and varied, while still maintaining the high-level valley and hill shape. And remember, this is just a sine curve. There's no randomness here even. This is what it looks like with actual Perlin noise. 1 octave, 2 octaves, and 3 octaves. We could of course tune the frequency and amplitude of each octave, but a good simple default is that each higher octave has double the frequency and half the amplitude. Alright, back to the code. I've now adjusted the Perlin noise class so that it takes the number of octaves as a parameter. That's it. Internally, it does exactly what I showed you. So when I call sample2d of x and z, it is actually doing 4 samples and adding them together, as I showed with the sine curve. The result looks like this. Much more interesting, much more realistic. And the code is still simple. The only cost is performance, because more octaves means the computer needs to work harder. There are ways to optimize that, but I won't talk about that here. Let's decorate this a bit, adding water and surface decoration and trees. Looks pretty cool, right? I find it amazing how far you can get with just a few lines of code when generating terrain in this way. However, there's still something missing. As we move around in this world, it initially looks really nice, but after a while it starts getting pretty repetitive. The terrain is random and somewhat natural looking, yeah, but missing more dramatic real-life features like cliffs, river valleys, plateaus, mountain ridges. Where is the drama, right? How can we make those kinds of things happen while still maintaining the smooth randomness? In the example earlier, we applied a noise transformation. When calculating the terrain height at a given position, we sampled the Perlin noise at that spot to get a value between -1 and 1. And then we transformed the value by multiplying by 20 and adding 100. The result is a surface y, in this case between 80 and 119. To make more interesting terrain, we wanted to enable more advanced transformations without making the code really complicated. And we ended up using spline points for that. I'll show an example. Let's give our noise field a name, continentalness. Each part of the world has a value of continentalness. It varies from -1 to 1. The purpose of spline points is to define how continentalness influences terrain height. For starters, I'll add 2 spline points. The first point says, at continentalness -1, the terrain height is 100. The second point says, at continentalness 1, the terrain height is still 100. Using these 2 points, the system will use spline interpolation to figure out the terrain height at all different values for continentalness. And that's just a fancy way of saying it will fit a curve to those points. In this case, the result is a straight line. Terrain height is always 100, regardless of continentalness. We have effectively created a flat terrain. But using this approach, we can now easily start shaping the terrain by simply adding or moving spline points. Let's say that a noise value of -1 means terrain height 50, and a noise value of 1 means terrain height 150. Fitting a curve to these points gives us a direct relationship. High continentalness means high elevation, and vice versa. In effect, this means continentalness noise directly represents the height of the terrain, kind of like where we were before. Again, not very exciting. Where is the dramatic terrain we're looking for? Well, okay, let's spice it up. Here we say that as continentalness goes from -1 to 0.3, terrain height goes from 50 to 100. A pretty gradual change. But then in this small span from 0.3 to 0.4, terrain height shoots up to 150, which is a very sudden increase. And then beyond 0.4, terrain height stays at 150. This tiny change of just a few numbers gives us a terrain that is completely different from before, with steep dramatic cliffs and plateaus on top. Pretty cool, right? To add even more variation, we actually use 3 different noises to control terrain height, not just one. We call them continentalness, erosion, and PV, or peaks and valleys, each with its own configuration of amplitudes and octaves. As you can see here in the picture, they look quite different. As you travel the world, each position has values for each of these noises. They are normally not visible to the player, but if you're curious, you can see them in the Java edition of the game by pressing F3 in a single-player world. So this is basically how we do it. This is how we generate the world. We've configured a bunch of spline points describing how these noises should influence terrain shape. For example, steep mountain ridges form where PV noise is high, continentalness is high, and erosion is low. When erosion is high, the landscape is generally flat regardless of the other noises. We've spent a lot of time fine-tuning these spline points to get just the right mix of terrain types. But the nice thing is that the code is actually quite simple and consistent, just a bunch of spline points. Here's an example, a relief map where you can see rivers and lakes and mountain ridges and all kinds of different types of terrain. This system is very flexible. It allows us to make dramatic changes to the terrain by changing just a few numbers here and there, and sometimes with very unexpected results. When we add biomes and surface decoration and features, it gets even more varied and interesting. When working on this, I felt kind of like Slarty Bartfast, a planet designer in Hitchhiker's Guide to the Galaxy, especially when working on the fjords. Okay, I admit, I've oversimplified things a bit. The stuff I've talked about so far is used to calculate the overall terrain height. But when it comes to the detailed shape of the terrain, that is actually done using 3D noise. Bear with me, I'll try to explain. The problem with 2D noise is that you can't get overhangs and super weird random terrain, the kind of terrain that Minecraft is famous for. So what is 3D noise then? How does that help us create super weird random terrain that Minecraft is famous for? Well, 3D noise just means a Perlin noise function that takes 3 inputs and gives 1 output. In our case, the 3 inputs are x, y, and z coordinate, and output is something that we call density. So each block position has a density value from -1 to 1. You can't see it anywhere in the game because it is used to calculate the terrain shape and then it is thrown away. Because it is a Perlin noise, the values change gradually, not suddenly. So what happens if we treat positive density as solid and negative density as air? You get a very strange but interesting world like this, some kind of crazy Swiss cheese cave world. Now let's apply a height bias. Density is decreased the higher we go and increased the lower we go. And there's a center point, say at y100, where density is left unchanged. This effectively squashes the terrain. When we are high enough above y100, density will always be negative, and hence there will only be air. And when we are deep enough below y100, density will always be positive, and hence there will only be stone. This is how the base terrain generation is calculated in Minecraft. It is controlled by 2 parameters, squashing factor and height offset. If squashing factor is high, we get flat terrain. And if it is low, we get fractured, crazy-looking terrain or even hanging blocks. Height offset moves the whole terrain up or down, so that is the base terrain elevation. Both squashing factor and terrain elevation are configured via terrain shaping, the thing I showed earlier, where spline points are defined based on continentalness, erosion, and peaks and valleys. So if you see some crazy looking terrain in Minecraft, that is because squashing factor is low, thus exposing the 3D noise. 3D noise is also used to generate the new cave systems. We use the same basic approach, giving each block position a density value. I'll illustrate it using 2D. Here's a noise field, again like the TV static, but smoothed out, right? If we decide that white is air and black is stone, then this already gives us cool looking caves. We thought this looked kind of like Swiss cheese, so we call these caves cheese caves. They typically generate large caverns like this, and the size and shape of them can vary quite a lot. To create long tunnels, we apply another variant of the approach. Instead of saying that white is air and black is stone, we say that the border between white and black is air and the rest is stone. This gives us long spaghetti-like tunnel systems, so we call these spaghetti caves. It is slightly different in 3D, but you get the general idea. These tunnels can get very long. We combine these two approaches to generate interesting cave systems with a ton of variation in size and shape. In fact, I still get surprised quite often by the caves I find, even though I've worked so much on this. Okay, I've talked a lot about terrain shaping, and I'm going to wrap it up by talking a bit about biomes. A Minecraft world is divided into distinct biomes, such as jungle or desert or forest. Think of the biome as a thin layer of material on top of the underlying terrain shape. For example, a jungle biome will add a bunch of jungle vegetation to the terrain, and a desert will add a bunch of sand. Biomes also control which types of creatures and features appear there. For example, desert temples can only appear in deserts, while igloos appear only in snowy biomes, such as snowy plains. Biomes have a major impact on gameplay experience. Here's an example of the same terrain shape with desert, meadows, grove, badlands, swamp, and jungle. They look completely different. So one important part of terrain generation is determining which biome to place at which position in the world. And how do we do that? Well, guess what? More Perlin noise, of course. Biome placement is done based on the 3 noise fields I already mentioned, plus 2 more, temperature and humidity. So each point in the world has separate independent values for continentalness, erosion, peaks and valleys, temperature, and humidity. And the values change gradually as you move around. The combination of values at each position, of course, determines which biome is there. And we configure that through a bunch of tables. I'll show an example. This configuration table is applied when peaks and valleys noise is high. That means we are potentially on a ridge or peak. To make biome configuration a bit simpler, we've taken the different noises and split the values into specific ranges. So erosion index 0 represents all erosion values from -1 to -0.78, for example. And yeah, we kind of sliced up the value space in this way. So let's say continentalness is high and erosion is low. This means we should use a peak biome. The specific peak biome in turn depends on the temperature noise. In this case, temperature was low, so we ended up with jagged peaks. A bit further off, we find a place with high value for peaks and valleys, so we are still on the same table. But over here, continentalness is low and erosion is somewhere in the middle. So this tells us we should pick a middle biome. And what is that? Well, that in turn depends on temperature and humidity, which is configured in this table over here. So we look at that, and in this case, humidity is high and temperature is high. So we're in a hot, humid area, and therefore we pick jungle. Unless weirdness is positive, in which case we pick bamboo jungle instead. Weirdness is yet another noise that I haven't talked about, but never mind that for now. Anyway, long story short, we use a bunch of configuration tables like this to specify which biomes should apply to which combinations of these noises. And when doing so, we take into account the terrain shape, the desired biome size and rarity, and also which biomes make sense to place next to each other. A lot of tinkering around. For example, we try to keep warm biomes like desert and badlands close to each other and not directly neighbor cold biomes such as taiga. Configuring this is actually quite tricky because it is effectively a 5-dimensional matrix that we are trying to put stuff into. That means each cell has up to 10 potential neighbors to take into account. Trying to understand this can be a bit mind-bending. It took me quite a long time, to be honest. But if you want to, you can pause and stare at this drawing until you either understand or go insane. Okay, let's wrap this up. So, what are the takeaways from this talk? Well, surprise! There are none. Or more like, it's up to you. I won't serve you any specific learnings or takeaways. I learned a lot when working with this stuff, and I hope you found it interesting. And even if you don't play Minecraft yourself, maybe you have friends or kids who do. And now you can impress them with your vast and deep understanding of how things work behind the scenes. Thanks for watching.